Welcome dear students in today's physics class. In today's class we will take up a new unit, and that is unit current electricity. And in this unit we will try to learn about these different topics. The first one is electric current, conventional current, drift velocity of electrons and current and its relation, then current density, then Ohm's law, resistance, resistivity, conductance and conductivity, and lastly we will try to learn about temperature dependence of resistance. Okay, the other things that we can discuss, these color codes of carbon resistor, series and parallel combination, this will be discussed in the next class. Okay, so let's try to see what is meant by electric current. We know that electric current is nothing but it is the rate of flow of electrons inside the conductor, right? So your electric current may be defined as what the charge flowing through any cross section of the conductor in 1 second, that means in unit time. Okay, so mathematically, if the rate of flow of the current, or rather the flow of electron, or rather charge you can say, if that is steady, then you can write the expression as what I is equal to Q by T, where Q is nothing but the amount of charge that is flowing and this T is a time taken. So if your rate of flow of charge is steady, rather in the case of what steady current, you can express this current I as charge divided by time. So if time is in the denominator, we generally define as what current as rate of flow of charge, right? But if the charge is not steady, that means if there is a change in the flow of charge, or rather if there is a variation of charge with time, then you can define this charge as what rate of flow of charge as small charge that is flowing through that small time. So we can define this what current I as dq by dt. Now let's try to see the different types of current that we find in our day-to-day life, and we can divide this current into two main types. The first one is what steady current, and the second one is what varying current. And in that steady current, what happen, as we know that steady means constant, uniform. So with time, what happen, the magnitude of the current will not what change, it will remain constant. So this, in this graph of this current versus time, this graph A will represent the first type, what we call as steady current. So what happen at different point of time, what happen, its current will remain same. So that is for the steady current. So the first type will represent by this graph A, that means for steady current, right? For varying current there may be various types. Okay, for varying current it may be either B, C or D. That means in the case of B, that means current what happened, increases with the time. So when time increases, current also correspondingly increases. Got it? So this is also what a changing or varying current. And another one is that you can take it this graph C also. With time, what happen, it increases, it again somewhere increases, rapid, very rapid increase in the current, and then what happen, it increases and then it decreases little bit and then it again increases. So as the magnitude of the current changes with time, what happen, this graph C will also come under this varying current, that means of whose magnitude varies with time. Number D, this is a special type of varying current, and we call it this type of varying current as alternating current. Why? Because in this type of current, the magnitude keep on changing. The magnitude of the current keep on changing continuously, and periodically it reverses its direction. So we call it such type of current, varying current, we call it as alternating current. This is number D. So your varying current That means if it changes its magnitude continuously and changes its direction periodically, then that type of varying current, we call it as what? Alternating current. Now let's see about that of drift velocity. Okay, what is meant by this drift velocity? Now before going further, let's try to take like this a diagram. Now suppose this is a conductor. Okay, this is a conductor, this is a conductor in the cylindrical shape. You can take it as a wire, okay, of length L having cross-sectional area A. If it is being applied by the source of EMF of whose potential difference is denoted by V, then what happened? Due to this applied potential difference, what happened? Electric field will be developed through this conductor. This side is positive plate, this side is negative plate. So you can think that electric field is applied from positive side of the conductor toward the negative end of the conductor, and in doing so the free electron present in this side, inside this conductor, will be moving from one end to the another end against the direction of the electric field. Got it? So this represents the electrons, minus circle, this represents electrons. So what happened when current is moving from the positive terminal toward the negative terminal in the external circuit? What happened? Your free electrons of the conductor will try to move from negative plate to the positive plate against the direction of the electric field. So what happened in doing so, these electrons will try to collide with such similar electron in its spaces. They will not move in a very straight line, rather they will move in a very zigzag manner. Rather the overall motion will be from negative plate toward the positive plate, okay, inside the conductor. So these electrons, okay, when it is being applied with a source of EMF, or rather the potential difference at two ends of its conductor, what happened there? This motion of the electrons will be drifted. Okay, these electrons will get drifted inside the conductor in the direction opposite to that of the electric field. So the average velocity with which these free electrons get drifted in a direction opposite to the direction of the electric field inside the conductor is nothing but it is known as drift velocity. So the definition is also given here. You can pause it and you can copy it down if you want. Okay, it is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of the applied field. Applied field is from left to right, whereas electron will be moving opposite to it. That means from right to left. In the diagram also it is shown here. So the force experienced by free electron, okay, inside the conductor is denoted by F vector, capital F vector, and it will be equal to what? E, capital E, where E is the electronic charge. We know that in the force experienced by this charge, F will be what? It will be equal to QE, right? QE. Got it? Where Q is a charge that is possessed, while E is the electric field through which your Q is placed. So what happened? The force experienced by this force will be equal to what? QE. But in our case here, for free electron, the charge possessed by the free electron is nothing but the electronic charge E. So it will be what? Minus E, capital E, where minus E is nothing but this is the charge possessed by an electron. Okay. Now what happened when this electron moves from one end to the another end? These electrons will try to accelerate, okay, in between two collisions. So before having any collisions during this short interval of time, this electron will try to accelerate, and whenever there is having a collision, then at that time it will decelerate again and again consecutively. Before having another collision within that short interval of time, this electron will again accelerate it. So the acceleration that is produced by the electron in between any two collisions will be expressed as what? A vector will be equal to the force divided by mass. We know that from Newton's second law of motion, force is expressed as mass into acceleration, right? So your acceleration will be equal to what? Force divided by mass. Force is nothing but this force, so it will be minus minus E capital E divided by mass. So this is the expression of acceleration of the free electron, okay, within that short interval of time or between any two successive collision, you can say. Okay, in other words, the electron accelerates for an average time interval tau. Now if you talk about all of the electron present inside the conductor, then we have to talk about the average. Okay, so average time. So average time, or rather average relaxation time, that means the electron will move in a very relaxed manner between any two collision. So we call it that time as relaxation time, and that relaxation time is denoted by what? Tau. If you take under consideration of all the electrons inside the conductor, then average relaxation time will be denoted by tau. So what happens if you are going to define this drift velocity? Then drift velocity not only of a single electron, rather for the whole electron. So drift velocity of the electron can be expressed as Vd is equal to U plus At, just like that in the kinematic equation, okay, in the motion. So what happened? Your drift velocity can be expressed as U vector, where U is nothing but this is the initial velocity of the electron, which is rather equal to 0, and your A tau, this acceleration relaxation time. So your A is nothing but minus E divided by m tau there. So what happened if you want to talk about this drift velocity only in magnitude? Then modulus of Vd drift vector, this will be equal to Vd without an arrowhead. That means this will give you only the magnitude, so minus sign will be removed and it will be E capital E tau divided by m. Got it? So your drift velocity is nothing but it will be equal to electronic charge times the applied electric field times the average relaxation time divided by the mass of an electron. Got it? Yes. Let's see the relation between this drift velocity and the current, and electric current, I mean. So this is just the diagram that I have shown you. So now let's see. Consider a conductor of length L. This is a conductor of length L. Got it? Having each cross-sectional area A, okay, uniform cross-sectional area A, and let V be the potential difference applied between the two ends of the conductor. Okay, then your electric field between the two ends of the conductor can be expressed as V divided by L, where V is the potential difference between the two ends of the conductor and L is the length of the conductor. Now this relation, you can also remember that your electric field is equal to negative of potential gradient, right? So only if you take it only the magnitude, then, and if there is no change in the potential, then we can take it as V by L, potential divided by length or distance. So potential difference divided by L will give you your electric field E. Now let n be the number density of free electrons inside this conductor. That means number density means number of free electrons present in a unit volume of this conductor. Then if you know this volume, then if you multiply that small n, number density, times the volume of this, then you will get it the total number of free electron present inside this conductor. Got it? So if n be the number of free electrons per unit volume of the conductor, rather you can call it this as number density of free electrons, then the total number of free electrons inside this conductor will be equal to n, that means number density of free electron times the volume of the conductor. Rather it is nothing but n into AL, where A is the cross-sectional area, L is the length of the conductor. Now again, if you know the total number of electrons, the total number of charge will be equal to what? This number times number of free electron times the electronic charge will give you the total number of charge. Got it? But suppose if an electron takes a small t time to move from one end of the conductor to the other end, then it will be equal to your time will be equal to what? Distance divided by the velocity. Rather, your velocity is nothing but a drip velocity. Got it? So your time will be equal to L by Vd. Okay, this will be, just remember all this expression. Q is equal to NALE, T is equal to L by Vd. Okay, we will use these expressions in the next slide. Let's see. In the next slide, see, according to the definition of the current, we know that current is defined as rate of flow of charge divided by time. We know it, that is a current. So we call it as rate of flow of charge. So charge divided by time. Charge is how much? NALE. Got it? The first expression in the previous slide. And T is what? L divided by V, distance divided by velocity. You can assume it in that way. So if you multiplied it, if you divided this charge by time, after replacing those expression of total charge inside the conductor and the time to cross from one end to the another end, you will get it as what? After cancelling LL, you will get it as what? I is equal to NEAVD. Got it? So therefore, the relation between the current and the drip velocity can be expressed as what? I is equal to NEAVD. For this, I have a mnemonic that you can take it this as NEP. I is equal to what? NEP. NAVDE, like that. You can remember it. You can take the mnemonic that all of the neutrals in the fetus inside the mother's womb, it goes from the mother to the fetus through placenta, and that placenta goes to that navel of that fetus, right? So you can remember it, that all the currents from the mother, that means the bloodstream, will flow through that navel of that fetus, right? So you can remember in that way, I is equal to NEP, NAVDE, right? Like that. So if you remember in that way, then you will not forget the expression of current in relation with this drip velocity. I is equal to NEP. It comes from the word navel. Okay, navel. You can take it that I is equal to NEP, NAVDE, like that. So what happened? I is directly proportional to the drip velocity. More the drip velocity, more will be the magnitude of the current. Taking under consideration what and what? This number free density of electron, number density of free electrons, electronic charge, cross-sectional area. As long as these are kept constant, then what happened? Your drip velocity and the current are directly proportional. That means what? Current increases with the increase of drip velocity. Now a very important one, that is mobility, and it is denoted by mu. Mobility may be defined as the drip velocity per unit electric field. You can define it in that way. Okay, so mobility of a current carrier is the ratio of drip velocity of a current carrier in a material to the applied electric field E across the material. That means BD by E. That means this is a ratio of drip velocity to the electric field. We call it that as what? Mobility. You can define this mobility in a very simple word as drip velocity per unit electric field. We call it simply that as mobility. Got it? Since BD is equal to what? EE. If you are taking only in magnitude, okay, drip velocity magnitude, then EE tau divided by M. So if you put this expression in the numerator, then it will be equal to what? E tau by M. Got it? E tau by M. So what happened? This E by tau M, the expression of mobility, is inversely proportional to the mass of the current carrier, right? The mobility, heavier the mass of the charge carrier, mobility will be less. So it is inversely proportional to the mass, okay, of the current carrier. Got it? So if this mobility, what happened? Higher the temperature, that means if temperature increases, then what happened? Average relaxation time will decreases and mobility will decrease. That means the movement of the free electrons will be restricted more and more, okay, with the rise in temperature that is given. Have you understood? If temperature increases, then these collisions will be very fast. The relaxation time will be less. Okay. If temperature increases, the thermal vibration will be more and more zigzag like this. Okay. So what happened? The time duration between two successive collision will decreases with a rise in temperature. So as tau decreases, what happen? This mu will be less. Okay. Mobility will be reduced. The movement of the free electrons inside the conductor will be less, and so what happen? The current will decrease. Okay. Current decrease. In another way, we can say resistance increases, you can say, right? Now let's see about the current density. Current density is nothing but this is the amount of the current crossing per unit cross-sectional area of the conductor. We call it that as current density. Rather, current divided by cross-sectional area, you can call it that as current density. And we know that I is equal to NEP. So if you divide that A with this denominator A, then you will get it only as NEVD only. In vector form, this is scalar form. Okay, in vector form, if you take it that current as I as current, in no doubt it is a scalar quantity. Okay, J dot A, you can take it J vector dot A vector, I mean. So if you take the dot product of this current density and this area vector, then you will get it current. Now your current, okay, your conventional current I is a scalar quantity, whereas your current density is a vector quantity. Through that cross section, perpendicular to that cross section, I should say, okay, your current flows across through it. So your current density is a vector quantity, and your conventional current or current is a scalar quantity. Now let's go to the Ohm's law. You might have learned in class 10 also. Okay, the electric current passing through a conductor is directly proportional to the potential difference, rather this potential difference across the two ends of the conductor when the physical conditions or physical parameters are kept constant. What are the physical parameters? Like that of temperature. Temperature is very important, and then mechanical strain, etc. remains constant. Okay, so if those mechanical constraints, mechanical conditions, okay, mechanical conditions like that of temperature, mechanical strain, okay, if these are kept constant, then what happen? The potential difference across the two ends of the conductor is directly proportional to the current. Got it? That is what I is directly proportional to V. In writing the statement, we generally write as current flowing through the conductor is directly proportional to the potential difference across the two ends of the conductor when temperature is kept constant, like that, no? But while writing that statement, we may write like this, but mathematically we have to write that V is directly proportional to I, because difference in potential difference creates current, not difference in current creates potential difference. Got it? Depending upon the difference in the height, the flow of the water from higher level to the lower level also changes, right? So likewise, depending upon the difference in the potential inside the at the two ends of the conductor, current inside the conductor may also depend similarly on to the potential difference. So potential difference is directly proportional to the current. You can have to write like this. You can write P is directly proportional to I, or P is equal to Ri. If you want to change this proportionality into equality, then we need a constant, right? If you want to change this proportionality into equality, then we will require a constant, and this constant is denoted by capital R, where R is a constant of proportionality known as the resistance of the conductor, and it depends only on the resistivity of the conductor. It depends upon, no doubt, the resistance of the conductor, It depends, it depends upon the cross-sectional area of the conductor, length of the conductor, nature of the conductor, and obviously on temperature also. But if you keep that temperature constant, cross-sectional area constant, length constant, then what happen? This R is a constant, and it depends only the nature of the material. Nature of the material means you can say also resistivity. Okay, resistivity, that means for different material like that of copper, if you take a copper, the resistance will be different with that of another material like that of aluminum, even though the dimensions remain same. Okay, dimension means cross-sectional area, length, if that is kept constant. Okay, so what happened, your potential difference across the two ends of the conductor can be expressed as what R times the current flowing through it, where R is the resistance of that conductor, right, or the material. Now if you are going to draw the potential difference versus current graph, then what happened, as we have seen that V and I are directly proportional, we know that directly proportional graph will be always a straight line. Okay, so and in this case what happened, your potential difference and current graph will be a straight line passing through origin. Okay, so this is the VI curve or graph given by Ohm's law, and those materials which follow this Ohm's law, that means B directly proportional to I, we call it those material as ohmic material. Okay, or you can call it them as having resistance to that of similar to that of conductor. So we can call it those material which has the property of this Ohm's law, we can call it them as having what, ohmic resistance, right? But in the case of semiconductor, they do not obey this Ohm's law. Rather, semiconductors are non-ohmic, transistors, diode. Okay, these are all non-ohmic what substances or material, you can say. Now let's see this resistance. If you want to express from that Ohm's law R, then it will be V by I, right? So this V by I, this means volt per ampere. The SI unit of resistance is volt per ampere, which is equivalent to what, ohm. That means omega. Okay, the SI unit of the SI unit of resistance is known as ohm, OHM. Okay, OHM, ohm, and it is denoted by omega, and this omega is equivalent to what, volt per ampere. Volt per ampere. Got it? Whenever there is a volt per ampere, then you can replace it by ohm. Got it? Resistance in terms of physical features of the conductor. Let's see the relation. We know that relation between drip velocity and the current, nap I is equal to nap. Then this drip velocity you can express as E, capital E, as we are taking the magnitude of drip velocity, you have to take it magnitude of electric field E. This we have already done in the previous slide, right? So you can express this E again by V by L. Okay, electric field is equal to potential gradient, you can take it in that way, V by potential difference by length, okay, or distance. So if you express it all those things by putting all those things, then you will get it I is equal to NE square A, what, this tau there, this is tau, actually it seems to be T, okay, but it is tau. Got it? So what happened, this one, then see tau, it seems T, but you have to take it this as tau. Okay, I is equal to NE square A tau V by ML. So if you want to express V by I, then it will be what, ML divided by NE square AT. Okay, that is what. So what is this V by I? V by I is nothing from Ohm's law, it is nothing but the resistance, right? Got it? So R can be expressed, resistance can be expressed in terms of what? ML divided by NE square AT, like that, A tau I mean. So what happened? Only this, taking this L by A, this mass of the electron, number density of free electrons in the conductor, electronic charge, average relaxation time, as long as you are not changing that particular conductor, these will remain constant, right? So this constant quantity we can express by resistivity rho. So R is equal to rho L by A. So your resistance is directly proportional to the length of the conductor. Your resistance is inversely proportional to the cross-sectional area of the conductor, right? But this resistivity of the conductor, that means it depends only on the nature of the material and independent of the dimension of the conductor. Okay, it is also expressed here, see, where R is equal to rho L by A, right? Rho is nothing but the resistivity, which is equal to what? Mass of the electron divided by number density of free electron, square of electronic charge, and the average relaxation time. Got it? This is known as resistivity, or you can call it as specific resistance. Specific resistance, why we call it as specific resistance? Because it is the resistance offered by a unit cross-sectional area, okay, through a unit length of the conductor. We call it that as specific. Cross-sectional area is also specific, unit cross-sectional area. Length is also specific, unit length. So that resistance offered by the conductor having unit cross-sectional area of unit length is known as what? Resistivity. In a very short way, resistivity can be defined as the resistance offered by a unit cube of that material. Okay, that is known as what? Resistivity. Got it? Resistance is directly proportional to length, as I said. It is also given here. Okay, inversely proportional to the cross-sectional area. Your resistivity depends only on the nature of the material, but it is independent of the length or dimension, breadth, thickness. It is independent of all those things. Because if you take a huge copper cube also, the resistance, we are talking about resistivity, the resistivity is not that of whole cube. Rather, we are going to take a unit cube, okay, that means of unit cross-sectional area of unit length. Okay, the resistance offered by that unit cube will be known as what? A resistivity. So it is independent of those length and all. Got it? Yes. Now let's see the relation between drip velocity, okay, resistivity, length of the conductor, electric field, current density, and a potential difference. So all those relations are all given here. As we have said that resistivity is what? Electric field divided by current density. We can express it, okay, in that way also resistivity. So your resistivity can be expressed as what? Electric field per unit current density. Now then it can be expressed as what? E is equal to your rho resistivity. Rho is equal to E by J. Okay, you need to remember this formula. E by J is also equivalent to the resistivity. E means electric field, J means current density. So current density, we know that it is what? A current flowing through cross-sectional area, I by A. Got it? So after cancelling I, then you will get it J as what? NEVD, right? So your resistivity and what? Your electric field or drip velocity, you can say, it can be related in this way also. Same is the case in the case of drip velocity. Got it? Drip velocity, I is equal to NEP, no? That one. So your drip velocity is equal to what? E divided by NE rho. You can express it in this way also. Why? Because here the reasons are all given here. Drip velocity is equal to what? E by NE rho, right? Yes. Then drip velocity can be expressed as V and E rho L. since what electric field is equal to V by L. If you replace it this E by potential gradient V by L, then you will get it like this. Now let's go to the conductor, and these are all also given here, as I said in the previous slide, that when temperature increases, Vd decreases and rho increases. Okay, like that, all are given here. Now let's see in the case of this conductance, what is meant by conductance and conductivity. You know, reciprocal of this resistance, we call it as conductance, and reciprocal of resistivity, we call it as conductivity. You see tans-tivity here, conductance, conductivity. So this conduct, reciprocal of conduct means resistance, okay, and conductivity, for this you have to take it as resistivity. Reciprocal of resistivity, we call it as conductivity. Reciprocal of resistance, we call it as what? Conductance. So conductance is a reciprocal of resistance, and its SI unit will be just what? Opposite of that ohm. If you read that ohms, OHM, no? In that way, if you read it in the reverse order, then it will be MHO. We call it this as mho, right? MHO. And this reciprocal of this resistivity, we call it as conductivity, right? So conductivity, the conductivity may be defined as a reciprocal of resistivity, and its SI unit is mho per meter, right? Because your resistivity is what? It is resistivity, SI unit of resistivity is ohm meter. So reciprocal of ohm meter will be what? Mho per meter, right? And temperature dependence of resistance. We know that resistance depends upon temperature. As temperature increases, what happen? Your resistance also correspondingly increases. Okay, then what happen? Let's try to see what will be the relation. Okay, now temperature dependence of this, as I told you, that when temperature increases, the average relaxation time decreases, because there is mobility, increase in the mobility. And what happened? Due to the thermal collisions, the average relaxation time decreases. As average relaxation time decreases, tau decreases. So what happened? R will be increasing. As tau decreases, as these two are inversely proportional, what happened? As tau decreases, R will increases. Okay, and the temperature coefficient of resistance. Okay, there are two types of temperature coefficient of resistance, depending upon whether resistance increases with the increase of temperature. We call it that as positive temperature coefficient of resistance. And if resistance decreases with the increase in temperature, then that type of material, we call it having what? Negative temperature coefficient of resistance, right? Now it is denoted by alpha. Okay, alpha. Now think that this resistance RT is the resistance at a temperature T, and R naught is the resistance at a zero temperature. So what happened? This increase in temperature, we know that R naught, this means at a zero temperature, or you can take it this as the initial temperature. And when you increase the temperature by, say, small t degree, then that resistance, let's denote it by RT. R naught is what? R naught is the resistance of that conductor at initial temperature. Say, let's take it as T naught. Got it? T naught. And a capital and at a temperature, if you raise the temperature of the conductor to T degrees Celsius, then the resistance that is having there in that conductor, let's take it as RT. Got it? So increase in temperature or raise in temperature will be RT minus R naught. From T naught, it increases to T, its temperature. So we know that when temperature increases, resistance increases, right? So rise in temperature, if you want to find out this rise in temperature, then RT minus R naught will be the rise in temperature. And this rise in temperature is directly proportional to the original resistance, okay, or rather the initial resistance, you can call it, and also directly proportional to the rise in temperature. Let me show you that one mathematically. Okay, so now let's take it that there is a conductor. Okay, there is a conductor like this. There is a conductor, and at a particular temperature, say let's take it as T degree. Okay, its any initial resistance, let's take it as R naught. Okay, R naught is where at 0 degree, when T is equal to, I'm sorry, this should be at 0 degree, or rather you can call it these as also what, initial temperature. So instead of this you can write it like this. Let me show you. At T naught, okay, that means this is the initial temperature. At T naught, what happened? The resistance, let's denote it by R naught. Now you hit this conductor through some temperature, let's take it as T degree Celsius. Okay, this is T naught degree and this is what, T degree. So at that T degree, we know that as temperature increases, resistance of this conductor will also increase, and that resistance of this conductor be denoted by RT. Which one is more, RT or R naught? Which one is more? Yes, RT is greater than what? RT is greater than R naught, right? So how much it is more, if you want to find it out how much it is more, then what happened, you can easily find out by taking the difference, right? By taking the difference. So taking the difference means what? RT minus R naught. So this is a difference. So this difference we call it as rise in temperature, rise in resistance, or increase in resistance. So this increase in resistance is directly proportional to two parameters. What are those two parameters? It is directly proportional, this rise in resistance or increase in resistance is directly proportional to the initial or original resistance. Okay, original resistance before rising any of its temperature. Okay, that is directly proportional to this R naught, and it is also directly proportional to the rise in temperature. The rise in temperature means what? R naught. This rise in temperature means T minus T naught. So what? T minus T naught. So this increase in resistance or change in resistance is directly proportional to what? Original resistance or initial resistance, and is again directly proportional to the rise in temperature. Okay, if rise in temperature is more and more, then what happens? Increase in resistance will be also more. So if we want to write these collectively, then we have to write this word in the form of product. That means this is directly proportional to the product of what and what? Directly proportional to the initial resistance times the rise in temperature. That T degree minus T naught is represented by this T. What is this T? This T is nothing but the rise in temperature. Got it? So if you want to express this proportionality into equality, then we will require a constant, and that constant is known as what? The temperature coefficient of resistance. If you want to write this proportionality into equality, then we require a constant, and that constant is known as what? Temperature coefficient of resistance. Got it? So if you want to express this alpha, then alpha will be equal to what? RT minus R naught, got it, divided by R naught T, right? Divided by R naught into T. So this is nothing but this expression is here. This expression. Got it? So how this temperature coefficient of resistance is coming, the formula, I mean, you will get it from here. Okay, So that is what. So rise in temperature or increase in temperature is directly proportional to the original resistance, as well as it also depends upon the rise in temperature. So if you want to change this that proportionality into equality, then you will have one constant alpha, and if you want to express that alpha, then it will be RT minus R naught, increase in temperature that was somewhere here, divided by R naught into T. Got it? That is how it is coming. So if you want to express this temperature as 1 2 like that, you can also express in this way. Got it? If this, okay, the final, you can take it this as an initial resistance and this as a final resistance, then what happen if your final resistance is greater than the initial resistance, then we call it that alpha as what? Positive temperature coefficient of resistance. Got it? Your alpha will be positive. But if your final resistance R2 is less than R1, okay, it is given here. If your final resistance R2 is what, less than the initial resistance R1, then what happen? Alpha will become negative, and that material will be called as what? Negative temperature coefficient of resistance. Got it? Okay, with that we will try to come to the end of this today's class, and in the next class we will try to learn the remaining those portions. Okay, thank you.